Chapter 11. Now, when Pontryagin developed his maximum principle in late 50s and early 60s, the translation in English translation, I think, came out in 1962, that the first people in the United States, other than engineers, just a second. Well, engineers and scientists, but the economics people were not far behind. So I think there are papers going back all the way to 67 that using 67, Carl Schell, Stanford at the time, and Aero or Harvard or Stanford at the time, were already applying optimal control theory to economic problems. Aero and Kurtz wrote a book in economics using optimal control theory. The entire book is almost like a first book on optimal control theory applied to economics problems. And then Headley Campus, another book came out, Takayama. So these are various books in, excuse me. And you will see that I worked with Canero on problems that extend this chapter, which is not covered in the book. The first model treated in economics was a model of optimal economic growth. The section 11.1.1 is a finite horizon fixed endpoint problem with a stationary population. And the problem is to maximize the present value, the utility of a consumption for the society, as well as to accumulate a specified capital stock at the end of the horizon. So I call it a fixed endpoint problem. Could be a free endpoint, but I just wanted to give a fixed endpoint problem an example in the book because we most of our examples are free endpoint problem, but here's an example of fixed endpoint. The second model incorporates an exponentially growing population in infinite horizon setting. And the reason I include that is because this is the first time that we will cover another method called the method of phase diagram. It's very popular in economics, and this is where we include this. Just so that I know that, yeah, let's talk about that. The extension of this problem of this second model, we'll talk about briefly, maybe for a minute or so later. Consider one sector economy in which the stock of capital denoted by KT is the only factor of production. Let Fk be the output of the rate of the economy, output rate of the economy, when K is the capital stock. This is called a production function. The production function is output as a function of the capital. It is a usual assumption on production function that F0 equal to 0, no capital, no output. And more capital, there is some output. And this output is increasing as capital increases, and that the marginal diminishing return on the capital. So this is the kind of a standard assumption on a production function. And part of the output is consumed. So if you look at the way the capital grows, K dot. Well, it grows because I produce out of the capital, so that's a total production out of the capital. But part of the capital is consumed, so I subtract minus C, and a part of capital depreciates. So K depreciates by this rate delta. We assume this to be a constant rate of depreciation, so the capital becomes older and less efficient, and we call it depreciation in economics. It's a standard term in economics. So the capital K dot equation is given by this, and we have an initial stock of capital called K0. Let U C, so what we consume gives us the utility. So let U capital C, this is the total consumption by the society. Let UC be the society's utility of consumption. And this is another standard assumption on the utility of consumption. Well, that one is not standard, but we will talk about this just in a second. Utility increases with C, and it decreases as a marginal utility is diminishing for C bigger than or equal to 0. Utility of 0 is 0, but that's also not clear. And the utility of 0 is not 0. Utility of 0 could be minus infinity if you consume nothing and you die, so you could be minus infinity. But this assumption is important. If u prime 0 equal to infinity, that means that at the zero capital, at the zero consumption, if you increase the consumption just a little bit, you have a huge amount of utility. That's what that means, which is true. So if you're starving, like no output, and somebody gives you a piece of bread, you get a huge utility out of that. You may actually live instead of die. So that's what it means. This also means that consumption will never be 0. So an optimal control will always keep the consumption bigger than 0. Bigger than 0 doesn't mean much bigger than 0. It simply means that it will not be 0. So we don't need to put the constraint C bigger than or equal to 0. Okay? And that allows us to solve the problem as a first order condition. Economics are very fond of first order condition. And after first order condition, they like the second order condition, but they never much appreciate for boundary conditions, boundary restrictions. So they want interpretation, and interpretation comes from first order condition, which is marginal revenue equal to marginal cost, etc., etc. So they want that. So anyway, this assumption is important for C bigger than or equal to 0. If it is not true, then boundary consumption can happen. And when boundary consumption can happen, the problem becomes more difficult. And this is a particular argument that got lots of people in trouble. In particular, in a consumption portfolio setting, the same thing will happen. And I will talk more about the importance of this and what happens later in the chapter when we do the stochastic control. That's where we will actually bring in this issue again later. So let's not spend time right now on this one. So this means you see strictly concave in C. Let rho denote the social discount rate, and let state D denote the finite horizon. Then a government which is elected at a term. So he is a short-term government. Biden is elected for 4 years, and he will only maximize what happens in those 4 years. He doesn't care what happens after 4 years. I mean, at least that is the one view to take. So the government which is elected to a term of T could consider this, but Biden can be nice enough to say, okay, I'm going to at least end my term with a certain amount of capital, which may not be 0, which may be a big amount if he's a good president. It could be a very small amount if he's not a good president. So that's kind of his idea of what we should end up with at capital T. This is a given constant. It's determined by us. And utility is determined by us. It's our utility. It's whatever. It may be noted that the replacing kt bigger than k will be the same. Because if I replace kt bigger than equal to k, there's no reason for me to leave more than kt. Because if I can use that little bit more to consume. In the worst case, I can consume at the end an impulse control, but just consume whatever is extra and get some utility out of it, right? And then leave it at kt. So you will see that kt bigger than equal to t and kt equal to kt in case is identical. They'll give you the same solution. The current value Hamiltonian is straightforward. Adjoint equation is straightforward. And this is the condition that we know, but we haven't used it a lot yet. But it says that if I have a fixed endpoint, then lambda t is free for me to choose. Okay, so it's some alpha to be determined. Okay, and we need to determine that as part of our optimal solution. Optimal control is given by first order condition, and this is absolutely true in this case. It's a concave utility function, so don't need to check the second order condition. And c is bigger than or equal to 0, so don't check the boundary. This is, in fact, the condition. And as I mentioned to you, this allows us to show that the CT is bigger than 0. This is not a proof. I'm just telling you. Proof exists in papers. I think one of the better proofs is in my paper with Karachaslavsky, Sethi Shreve, published in Mathematics of Operations Research. So that's condition that we can see. The economic interpretation of Hamiltonian is straightforward. We know this. This is general. We already know it consists of two terms. First one gives the utility of current consumption, which is UC. And the second one gives you the additional output and the value of the additional out given by lambda. So when I use a control C, I get some output, and that output is valued at lambda. So for any C, I get this utility and then the output. If I consume more, I get more utility here, but I will get less k dot, and so there will be less value here. And so I can think of maximizing Hamiltonian with respect to C to find the optimal consumption. And this gives me a dynamic condition for optimal consumption. And this lambda converts the problem into a static problem at each point in time. Okay, so that's the whole idea of the Hamiltonian and the control theory. So that's the condition on the Hamiltonian, first order condition. But there are other three conditions that Mr. Arrow also interprets in his book. One is called the static efficiency condition, which is already talked about, that at each point I maximize the Hamiltonian given the lambda t is known. That's because the lambda t takes into account of the future value of the increases in capital. The second condition is dynamic efficiency condition, which is the lambda dot equation, which is rewritten this way. It says that the capital gain plus the amount of production that I get in the interval small dt is equal to the social discount rate on that amount of. So suppose I have 1 unit of capital. 1 unit of capital has a value lambda, and that lambda, if I want to earn the rate rho, then in dt amount of time, that's the amount of money I should get out of that investment in a bank account. On the other hand, if I don't invest in the bank account and I use it for production, then I will have a capital gain of that unit. There may be price differences in the next delta t interval, that's d lambda. And I'm producing with that capital, which gives me this. So that total amount should be equal to that amount. In equilibrium, I cannot earn more than the social discount rate. And that in fact, what it is saying is that I have to select lambda in such a way that I cannot earn more than the discount rate. So it is in fact a condition on lambda, but you can also see what is a dynamic efficiency condition. And finally is a long-run foresight condition, which says that I must choose alpha in such a way that I should choose this. Oh, I'm sorry, what's going on here? I should choose that alpha in such a way that when I solve the problem, I will end up exactly at KT. Okay, because that's what I want to do. So those are the three interpretations of the three conditions. You can solve that as a 2-point boundary value problem that is shown in exercise 11.1 for a different model where utility function is given to you and f is given to you. So now we have a more standard model. The model is model of two-sector production. This two-sector production says that production function is a function of capital and labor. Okay? And labor in this model is given to grow at the rate g exponentially. So I have this amount of labor at L0, and it's growing at the rate g. So at time LT, the labor that the society has is this amount. Okay, basically it's a birth rate in some sense. So that gives you the number of people growing. Now we assume some conditions on this production function, which are standard. We assume that it increases with K, it increases with L, and it is marginally diminishing with K and marginal diminishing with L. So that's true. And those are the minimal conditions. The cross derivatives FKL could be anywhere, okay? But there's another one, it's called the degree. Homogeneous degree of 1 means that if I multiply K by M and multiply L by M, then my product should be M times FKL. The argument is like this. Suppose I have a factory which has a capital K and a labor L, then that factory is producing this amount. So I can start another factory with the same K and same L, it'll produce this amount. So now I have 2 times FKL. So if I have 2 factories, I have 2 times FKL. So this is called the homogeneous degree of 1. But you don't always have this in different production functions. Some of them may be not of degree 1, which is saying that if I have multiple factories, there may be it could be that the multiple factories are so difficult to coordinate. And by doing all of these, I may not be producing M times that much. So that's one argument that one can make. The other argument you can make is there may be a synergy that is coming out of these factories. And so it might be more than 1. So homogeneous degree can be more than 1 or less than 1. But in our model, we're going to assume 1. Okay? It's a standard assumption to assume 1. If you assume 1, then what I can do is I can define the capital labor ratio to be K equal to K divided by L. Then I divide this production function by L. So if L is 1 divided, if M is 1 divided by L, then I can put this L inside because by this formula here, then I get this. And I call this to be small k, so I get this. But this is constant, so I can define this by simply f of k. So I call this f of k. So what I'm trying to say is that if I have 2 sector economy with capital sector and a labor sector, then if the labor and a capital, if the production function is homogeneous of degree 1, then I can construct another production function which has only one variable, so I can almost treat that as a single sector, okay? But that also requires this. So there's another thing going on. So we'll see what happens. So I take k of dot, and I get k dot L plus Lk dot, L dot k. And L is G of L, G times L from this formula, because L dot is growing at the rate G, so L dot is GL. And I can substitute for K dot, this K dot, from 11.1. Let's not go back. It's easy to. And I can find this equation. You can now see what's going on. This equation is almost the same as our original equation, Fk dot. See, Fk minus C minus delta K. Now see what's going on here? Small k dot is Fk minus C minus gamma k. So the only difference is this gamma. Instead of delta, I have a gamma. And a gamma now is G plus delta. So you can see the following. The capital depreciates by rate delta. But the per capita capital will depreciate more than by rate delta, because population is growing. So the per capita capital is decreasing by G because of the population growth. So population growth decreases the per capita capital at rate G, and the capital is decreasing at the rate delta. So the total net, the net depreciation is G plus delta for per capita capital. So mathematically, this model is the same as the previous K dot equation. Let's see what happens to the utility. I'm now going to define per capita utility, not utility, but consumption, C equal to C divided by L. Now let's take UC with the utility of per capita consumption. Each person has a utility, that's what it means. And this has the same condition as any utility function that we assume, except this condition could be relaxed, but most people would assume this. If they don't assume this, likely they're going to make mistakes unless they're very careful. So now there's a number of ways we can deal with this. How do a society defines its utility? Well, one way to define the utility is called the total utilitarianism. Benthams and other people who have philosophers, they argue for total utilitarianism. That means that I multiply the utility of one individual by the total number of individual population, and I will call this to the utility of society. So everybody gets some utility, and I sum these utilities, and that is the utility of the society. Okay? The argument that you can make is that that may not be a good model for the society. I'm just now giving you something beyond what I wrote in the book. And there are different arguments to make. One argument is that if you take the total utilitarianism, then it is a possibility that the population is growing to infinity and the consumption is going to zero, but the multiplier of the utility and the consumption is still quite large. You can have everybody very poor, but lots and lots of poor people, and the society has even a higher utility, okay? So, so suppose there is a country that has 100 people and is very rich, everybody is rich. But now let's take another country that has 1,000 people and everybody is 10th as poor. The utility of this country and the utility of this country is the same. But here everybody is 1/10 poor, but there are many, many people. Okay? So what would you consider to be a good thing for society? Now suppose you take the utility of per capita consumption as the measure of the society. Well, if you take the utility of per capita consumption measure of the society, now notice now here, I'm now arguing to you in a slightly more general setting. I'm arguing to you that the countries not only have a control on capital, but the countries also have a control on population, right? Look at what China did. For years ago, it says, well, single child policy. Look at what Japan does, baby bonuses. Okay, you give more money to produce more children. You know, okay, if you make 2 children, I'll give you so much money. So countries have, manipulate or control population. And right now in this model, I don't control the population. Control population is given, but the model that I'm extending, which I did with work with Kenneth Arrow, is is going into that direction. Okay. So if that's the case, and if you want to maximize per capita utility, you could make an argument that an optimal society would be to have a lot of people die and remaining people become very rich. And the optimal solution, or the equilibrium, could be a model of a king. One king is the only guy who survives in the country. The rest of them all died, and the whole country belongs to this king. So he has an infinite amount of, not infinite, but a huge amount of consumption possibility, but just one person, and that maximizes the utility of the society. So you see, either argument of total utilitarianism versus per capita consumption are having problems. And the issues are more ethical than economic. I mean, if you take the per capita argument, you may say that it might be optimal to kill a few people, right? So that the rest of them can live better. And some people have proposed that, by the way. It's not unheard of that people have looked at this kind of stuff in the philosophy. Okay, this is not our purpose, but all I want to tell you is this, that my second edition, I had a per capita consumption model here. And I changed that to the total utilitarism in this book, because I think the total utilitarism makes a little bit more sense, especially if the problem is, it makes a little bit more sense than having an equilibrium of a king. Okay. So if you take this approach, then I can substitute for LT L0 e to the GT, and then I can take that outside. L0 can be outside, and I have a e to the GT here, and e to the GT and this rho becomes G minus rho. Okay, so I can define the R to be rho minus G, because I'm going to take minus R, and because e to the minus RT. So now I can, and L0 is fixed. So I'm maximizing this. In this model, L0 is fixed, so I'm actually maximizing this, where R is given by rho minus G. So now notice what happens. My model is maximize this subject to this. But this is almost mathematically, not almost, mathematically, it is the same model as the previous model. Because the previous model, I also had some rho here instead of R. So I've changed now rho to R. So this is one change. And I've changed this delta to gamma, which is another change. So make these two changes, I convert that model into this model. Okay, so the solution of the two, if it was a finite horizon problem, is almost same, except the parameters are different. So the mathematically they are the same problem. Solution will be different because the different values of the parameter, but mathematically the problem is the same. So what is new that I want to bring it here is the infinite horizon. So how do we handle an infinite horizon in this particular setting? And that's where a method of phase diagram comes in, and I'm introducing the method of phase diagram to you in this chapter. So let's go there. Hamiltonian, same as before, the previous section, same as previous section, same as previous section. So all of these are same. Lambda dot is also same as previous section. Now what happens is we solve this for C also as before. This C is now h of lambda, which is the inverse of u prime inverse lambda. Remember, u prime is monotone because u double prime is strictly less than 0. So u prime has an inverse. If it's monotone, strictly monotone, it has an inverse. So inverse is well defined. So h alpha is a well defined function. And you can write this as you can write this as u of h of lambda equal to lambda, because if you take the inverse, it becomes u of h of lambda equal to lambda. And then you take the derivative and find the value. You can actually find h prime lambda simply by calculus. So in calculus, so this is same as writing u of h lambda equal to lambda. That's what it means. That equation means u of h lambda equal to lambda. Okay. And then you take the derivative u prime lambda times h prime lambda equal to 1, and then you can easily find out that h prime lambda is less than 0. Oh, here. It's already here. So again, because of the concavity and the maximum principle is also sufficient because the sufficiency condition goes through. So we are now working towards the phase diagram. We want to know what characteristic this function, how does C changes with respect to lambda. We like to know that. And so all of that is coming to this phase diagram kind of method. This is a maximized Hamiltonian, and we know this is concave, and so we can also handle that. So this is the phase diagram. I am now going to apply C equal to h by lambda I can substitute that into our two equations. So we have these two equations, and I now want to find a stationary solution, like a turnpike. Okay, that's what I want to find out. So I want to find a stationary solution where k dot is 0 and lambda dot is 0. And I can easily find that point. I can prove that in functions that I have, there's such a point exists. And then I need to find out that from any initial value of k0, I can select a value lambda 0 so that these two equations will converge to their solution. So let's look at the picture. So this is lambda dot equal to 0 equation. If you go to lambda dot equal to 0 equation, you can see lambda goes out, and this becomes f prime k equal to r plus lambda, and that is basically a straight line here. Gives you k bar. That gives you f prime k equal to r plus lambda gives you a value k bar, and that k bar is this equation, this line. So lambda dot equal to 0 gives you this line. K dot equal to 0, on the other hand, gives you this line. So you have an exercise to show you that because they're functions, we know their derivatives and everything. You need to find out what is the shape of k dot equal to 0. The k dot equal to 0 has a shape like this in the lambda k space. And in exercise, you're supposed to find out that it first decreases, then increases. Okay, that's the thing you want to find out. Now, if that decreases, then increases, and this is a straight line, then it's easy to figure out that there is an intersection point, and the intersection point is k bar lambda bar. So what the economy is trying to do is, suppose somebody gives me a k0. If somebody gives me a k0, then I should solve the optimal control problem to find a lambda 0. If I find a right lambda 0, then that point is lambda 0, k0 is this point. And starting with this point, I should solve these two equations, not zero equation, but k dot equal to this, k0 equal to k0, lambda dot this, lambda 0 equal to lambda 0. So with that beginning point, I can solve this and I can find a trajectory of k lambda. That trajectory of k lambda is like this trajectory. If I have a right lambda 0, this trajectory will converge to k bar lambda bar. And then I stay there. That's called a growth path. This is a turnpike theory in economic analysis. This is where the turnpike started. Turnpike argument started in the optimal growth model. And now we use the turnpike in our advertising problem in chapter 7 and other places. Okay? But turnpike idea came from the turnpike theory in economics, which is basically growth theory in economics. If my k0 was here, then I should find a lambda 0 here so that this converges to this. If I find a lambda 0 not there, but here, then I'm here at this point. Okay? I have to show that at this point it doesn't converge. And I have to show that this point doesn't converge. That only point it converges this point. So there's only a unique value of lambda 0 that I have to find for which this convergence takes place. Same thing on this side, okay? Okay, so this is the goal, okay? This is the goal. And now the next thing is, is there a possibility, is there a lambda 0 such that this convergence takes place? And there are many ways that people have proved this. And in my second edition, I had a different proof. In my third edition, it's a different proof. And I may not even give you much of that proof because there's a general theorem that I also include in the third edition. And one can just use the general theorem to say that this is true. Okay, so we will give a little bit of inkling of how I'm deriving this because it's in the book. And it's also used by one of our papers. But I also want to tell you that most of it is standard. And if you were to write a paper and do a phase diagram, you don't have to do that proof. Generally speaking, you just give the theorem. And I will show you the theorem as well, called global saddle point theorem. That will also be part of this. Okay. The proof goes something like this. Well, we know the lambda dot and k dot equation. We know their right-hand side. We can actually show that these two curves results into 4 different areas in this quadrant. One area is this area. This is surrounded by this and this. That's called quadrant 1. The other area is like this area. This is called quadrant 2. The third area is this area, which is quadrant 4. And this quadrant, this side is 3. So 1, 2, 3, 4. 4 quadrants. Each quadrant, if I begin with a point, I can show that, and I'm just giving you a very big picture now, and then we'll just put everything together. If I'm at a point here, I can easily conclude that lambda x, k will increase. So if I start with this point and I solve these two equations, then x will increase and lambda will decrease. So this is this arrow that says what is going to happen. If I'm at this 2 point, then lambda will increase and x will increase. If I'm at this point, then x will decrease and lambda will increase. If I'm at this point, then x will decrease and lambda will decrease. So that's that. Okay, we can find out this by looking at those equations and functions. Once we find this, you can sort of see what's going on. Okay, so if I have a k0 here, okay, then it's clear that the lambda 0 cannot be in this quadrant. Because in this quadrant, if I'm here, this curve will go like this. If the curve goes like this, it cannot come here. So we rule out this argument. This quadrant is not going to work. On this side, this quadrant is not going to work because if I put it here, the path will go like this. If the path goes for any point like this, then only at this point in this quadrant is going to stay there, right? That's the only point is going to stay there. But any other point, it will go like this. So this quadrant and this quadrant is not good for our problem. So lambda 0 for this k0 has to be here. And if k0 is bigger than k bar, it has to be here. So you can see that one is going this way. That one is going this way. You see that? So now if I choose this way, then what happens? I go like this, and I will eventually hit this line here. And as soon as I hit this line here, this one operates, and I will go like this. So if I start from here, my trajectory will go here, and then it will go there. So it's not going to converge. If I start here, then I will go like this, and I will hit this dotted line, or this line. And then once I hit this line, this will operate, and I will just go like this. So I will go like this and like this. So you can see if I start from here, I will go this way. If I start from here, I go this way. And so there is some point that I will hit exactly this point. Not don't hit there, don't hit there, exactly hit there. That's it. That's what we are after. We want to find out this path. That means this initial condition. And once I find this, I can find this path. Once I can find this path, then I can find for every k0, I can find a lambda 0. So if I given a k0 here, I go here and I find lambda 0. If I'm k0 here, I know lambda 0. If I'm exactly here, then I can just find lambda bar and I just stay there. If I'm exactly on turnpike, I just stay there. Okay, so you got the idea. Now let's put it together. Okay. So you have exercises here that shows the dotted curves are the graphs of k dot 0 and lambda dot 0. We already did some of it. And then you can show that there's a unique solution, k bar lambda bar, of these two equations. The unique solution of these two equations, k bar lambda bar, is just this point. So that part is this part. Now the second part is to try to get these guys. These guys are rather straightforward. I do one and then exercises are given you another one. So these things are called isoclines. The two isoclines, these isoclines divide this into 4 parts. We already talked about this. So you can see to the left of the vertical line, lambda dot equal to 0. This is the vertical line, lambda dot equal to 0. To the left of this, what are we seeing here? We're seeing for the left of this, remember lambda dot is r plus gamma equal to f prime k. So for the left of this, we have k less than k bar, and given the sign f prime k, we can see that for k less than k bar, r plus gamma is less than f prime k, because f is increasing. Okay. So r plus gamma is less, f prime k is less than r plus gamma. No, f prime k is decreasing because f double prime k is less than 0. So f double prime k is decreasing in k. So when I look k less than k bar, then this is going to be bigger than r plus gamma. And so we have this. When it's bigger than r plus gamma, in view of this guy, then we know lambda dot is less than 0. So what did we get? We're saying on the left of side, for any point, lambda is going to decrease. So you see lambda is decreasing and lambda is decreasing. Similarly, on the right side, from the same argument, lambda is increasing and lambda is increasing. So we already got the half of these for 8 arrows, okay? So we got that. For K, I'm asking you in exercise, you're asked that the horizontal arrows which indicate the direction of change in K point to the right above K dot 0 and left to the below. So what we're not, in exercise, you're asked to do that the K dot is going to increase above this line and is going to decrease below this curve. And then we get all this. So we got that part. Now the third part, the next part is that there's only one such point. Here you'll go this way, you'll go that way, and that's this part. So this is the next part. Now, I'm going to give you pieces of this argument, and then I will go to the theorem, okay? And you can read this. We are not, if you write another paper and you use this, you can use this argument or you can just use the theorem. So for that, you know, how lambda changes with respect to k, one way to do is d lambda dk, which you can find is d lambda dt or dk dt, which we know all of these. And so we can write this. So that's first part. Then the problem is that this is 0 and this is 0 at this point. Notice now, this is the argument that we have in the paper that we wrote recently for a more general model than this. So we are here now. And we find lambda prime k. Okay, it gives me the sign. It gives me the value by doing this. But the problem is that at lambda bar k bar, this is 0, this is 0. So at lambda bar k bar, or at k bar lambda bar, at here, the sign is 0 by 0. If the sign is 0 by 0, so let me tell you what is going on here. Here's what is going on here. Some people will make argument like this. Some people make argument like this. Okay, that's one way to show there's a unique, but that requires some theorems in mathematics. And second edition, I did that, but I did not want to use those theorems. So I go through this argument. This argument says that if I begin here and solve those equations from, this is the beginning point, and solve this equation from here, then I will go a curve in the opposite direction. So I will go on this curve in opposite direction. Instead of going from here to here, I'm now going from, because I know this point is, I'm coming to this point. So if I start from this point and I go this way, then I will have the whole curve. And once I have the curve for every k0, I will have lambda 0. So it's done, right? So I begin with it. But the sign is 0 by 0. But if you have a 0 by 0, you do L'Hopital. You find out what is the value. Because I need to find out how to go up. From there, I need to find out how to move. Because if it's 0 by 0, I don't know how to move. I move this way, this way, this way, this way. Because I don't know what 0 by 0 means. Okay? So I have a 0 by 0. So that two things you do to get there. One is that you subtract. This is our 0 by 0, and I can write it this way. How do I write it this way? I simply subtract the value at k bar, which is exactly 0. So what I do is from this I subtract this at k bar, because at k bar this is 0. So I can subtract 0 without doing anything. And for lambda dot, I subtract this for lambda bar. So I can subtract what is already 0 at k bar, but at another k it is not. So for any given k, I can subtract the k bar part. So this is same as this because I subtract 0 from there, subtract 0 from there, so I should not make any difference here. So this is what I got that. So this is first part. The second part is that this is 0, this is 0. So I will take a L'Hopital. I take the derivative of this relates to k and derivative of this relates to lambda. So this is my L'Hopital rule, sk to k bar. I can find lambda prime k bar by taking the derivative and derivative, derivative of k, derivative of this, it continues to this. And for that, I use the argument of h prime, which we can easily compute. So I use that. And once I do all of these, I get this equation. So now I know the value of lambda prime k bar, and I can get the slope at k bar. The slope is given by this formula. Okay. And this is not 0. It's a limit of 0 by 0, so I have it. And then I can solve the differential equation. And when I get to that, I can show that there's a convergence and there's everything is defined. Everything is done. So that's kind of giving you the sketch of this. Now I'm going to give you the theorem, which is this. Let x bar lambda, this is now for any general control problem. So this k that we have is now x because x is a state. Let x bar lambda bar be, this is by the way an appendix. Go to the appendix D, you will see this. Let x bar lambda bar be a unique saddle point of the system, which is the system of differential equation equal to 0. And let x0 be the initial state. Okay. And vertical line, this intersect both this. Assume further that the region is bounded by ascending line is, and the line x equal to 0 has a triangular shape. I will give you the picture. Then there exists a unique saddle point path starting from x0 and leading to the saddle point x bar lambda bar. That's all we need to do. That's all. We're not computing lambda 0. We're only showing that there exists one. So here's what's going on. Here is the point x bar lambda bar. And here is x dot equal to 0. And here's the lambda dot equal to 0. And they intersect here. And here is a straight line going up x0. And what the theorem is saying is that if this x0 line and these two isoclines forms a triangle, see the triangle here? This is a triangle. If they form a triangle, then there exists a lambda 0 such that you will get it here. That's all we're trying to prove. So it says if you go here, it will escape. It will go here, it will escape. But if you go exactly at this point, it will get there. So the nutshell is that we can actually do this for our model, and we can prove that there is such a point. So in sum, we have a phase diagram method and a global saddle point theorem, which is a general kind of argument for this. So we don't have to, each model, we don't have to do something. If this triangle thing doesn't always work, then maybe you have to go through the main argument. Or maybe there are other things that will take case of this triangle because this is a straightforward argument. Okay, so that's basically what's going on. And the reason I'm shortcutting this a little bit because I think this is all you need for research papers and everything. I already give you the sense of it. So the sense of that is that you get the direction. You get the direction, so this becomes your initial point, and you solve the differential equation backward, and you can show that differential equation has a solution. So that gives you theorem of differential equation, which is in this case is in most cases of real life problems, you will have a solution in some sense, but you can, there's some argument that I made, so I don't want to get into that. And the reason I also did that is because the material that I didn't cover before, and I don't know whether in my outline, whether I said it is covered or not, but given the epidemic, that situation we are in right now, I also want to cover this. So the section 11.2, maybe it is, yeah, 11.2. I will cover 11.2. I don't know whether if it's an outline included or not, but given that we are in pandemic, I like to cover that paper. I also want to mention that I'm not new to pandemic. I have actually done simple pandemic control models in 1974 and 1978. This was, by the way, one of my students in control theory course, and in 78 or 77 or whatever, I was teaching this course in, no, I was teaching this course earlier than that. And in the earlier lectures on this course, I wanted every student to write a paper. And some of those papers be published. This is one of the paper published with one of the students. And this student actually moved to Dallas area, and I actually had a lunch with him some time ago. There's some other paper that I published with the students on other papers that were done in that class, but now I don't require you to write a paper because many simple papers have already been written, and more complicated papers require a lot more effort than can be done in a class. So I don't require this paper anymore. But in the earlier part of the courses, we used to do that. Okay, so this model we discuss is my model. Okay, and I use Green's theorem for this model. I published that in one of the top journals in bioscience or whatever it's called, and I'm covering that. I will also send you a paper that we are working on right now, which is way more elaborate on epidemic control with some data, and that model is use maximum principle, and it cannot be solved analytically. So we solve it numerically. And so the model is being developed by me and a professor in France and a professor in Israel. The Israel guy is the main numerical guy. That paper is currently under major revision at PALM in the second round. But I think after I cover this model, I think that model is available at SSRN or something, right, Kushali? Yeah, it is available in SSRN in a medical this thing. So Kushali can send you the link of that paper. Okay.
That's the one with Fawad, right?
With Fuad and Eugene.
Yes, I can send the link.
Right.
Or the PDF of the paper too.
Right. So in the remaining 4 minutes, let me try to do as much as we can on this paper. It's
you
actually
have 17 minutes, Professor. Class ends at
yeah,
3:45.
17 minutes. So I can definitely cover it. Okay.
17 minutes.
Okay, that's no problem. So this paper is interesting history in the sense that when I was teaching the course at Rice University, somebody wrote a paper and I wanted to grade that paper. In order to grade that paper, I had to go to the library. And I went to the library. I had to look for epidemic literatures. And that's the paper that I was grading. That's a different model. But in order for me to do that, I had to understand a little bit about this. And when I understood a little bit about this, I found a paper published on a disease of eye called glaucoma. Glaucoma is an infectious disease of the eye. And the guy develops the model, but he doesn't solve it. So I said, okay, this is an optimal control problem, so I should be able to solve it. So this is almost like the Vidal-Wolf. I did the same thing. I was looking for the advertising literature, and I found that Vidal-Wolf did not solve the problem. And so I found a control theory problem. That was 1973. And in 5 years later, I published this paper using, again, Green's theorem and finding a model that was in the literature and was not solved at the time. So let's quickly do that. The model is like this. The model published in the literature is this. It says that if there are total fixed populations n, and the number of infectives are x, then n minus x are the people who are not infected. They are susceptible. So infected people interact with the susceptible people, and they transmit the infection to these guys. And beta is the infectivity, how fast. For example, the UK virus has a bigger beta than the China virus, whatever it's called, the coronavirus, a virus from China. I don't want to use the Trump's terminology, China virus. I'm just going to call you that is the virus that came from Wuhan, and the other virus came from UK. And so beta is higher for UK than for that. So this is the beta. And then the people, a certain number of infected people get cured. Okay? And so that is our control variable. We can increase the cure rate by curing people, and then we can decrease the number of infected people at a faster rate than without that. Without that, this is the model. And then sometimes infected people die. So this is called a SIR model. It's a very popular model that came into being in 1930s, and it's become a standard model in epidemics. SIR means susceptible, infected, recovered. SIR. Now, of course, there are more compartments, but that's how it is. Okay. And you can find out R0 for any model. There are formulas for that. Okay. So all we need to do to solve this problem, to make it a control problem, is to include the objective function. By the way, this is all I learned from the library. Now I'm going to do the objective function. So I'm going to say that there is the infected cost to the society, which is H times X. It's a social cost of, mixed labor, mixed production and things like this. And also late homeworks, not for the social cost of infective, but the people are literally infected by the vaccination for at least a few days. So there is a cost. And there's a cure, and I have to pay money for the cure. So this is M times V. And I want to minimize the cost, so I'm going to maximize the negative of the cost. And I'm going to shoot for a terminal constraint of xt, where the infection people are so low that we can call it we can call it that there's no more infection going on. The R0 becomes so low that the infection will die. And there's a discount rate for the cost. And I put a control cost because I cannot have an infinite rate of cure. So I'm going to put a control Q. So you can see this is now I can do VDT. I can convert that to line integral, just like we did in chapter 7. And then once I have a line integral, I can use the Green's theorem. I get the integrand I, and I set that equal to 0. I get x bar. Okay, so I have my turnpike. Okay, once I have a turnpike, there's a slight issue here, which is that the turnpike itself may not be feasible. So if 0 rho theta is less than n, the turnpike is rho by theta. If it is not true, then turnpike is n. Okay. The corresponding singular control for this one is V of S, which is given by this. And if everybody is infected, then what is going on here? Vs is 0. If everybody's n is infected, infectivity rate is so high that there is no point, at least in this particular case, no point putting any medical effort. So once we have that, we can find the control which is the most rapid approach path. And there are cases, different cases, just like in chapter 7. And let us look at one of them. So here is the turnpike. Here is another, notice here that there's n by 2 where there's an inflection point. You see the inflection point. So V star equal to 0 when you don't use. It doesn't just go up like this in the chapter 7. It goes and then it goes this way. So there's a little inflection point. So if my inflection is very high, I go like this. And then I go here. And then I go back here to get to xt. If I'm here and what am I doing here? If I'm XS here and just 1 second, there are different cases here. So this is X0. This is also X0, but I don't label it X0. That is not good. So I should label it X0 and it goes like that. So there are the functions, as you can see here. Actually, the opportunity is shown in this. It can be shown that x goes asymptotically to n minus q beta if time is infinity. So if you go to here, you can sort of show that this actually will not go below this number. As t goes to infinity, this is an asymptote. So that is all algebra that you can find out. And so we basically solve the problem in different cases here. And of course, t large, we're assuming t large so that we have a chance for this and chance for this. If t is not large, then it will go here and then go. And we did that in chapter 7. What else is here? Assume this is less than n. Assume that t is large, so the trajectory will spend some time. And q is so large that x is always going to be bigger than this. Graphs are drawn for these cases. And let's see, what else do we see here? Yeah. When this is less than 0, you're asked to exercise that x is equal to n. So this is one thing. In this case, what happens is h by m is less than beta, which means the ratio of the social cost to the treatment cost is smaller than the infectivity coefficient. Okay? And therefore, in this case, when there is no terminal constraint, the optimal trajectory involves no treatment effort. An example of this case is the common cold flu. No, not flu, common cold. Common cold meets this criteria. Okay? The social cost is not that large. And the treatment cost may be liberalized. But what is going on then is that you don't treat anybody. People just recover from common cold at home. We haven't even found a medical thing for common cold. There are tons and hundreds of viruses that cause common cold, so people don't even have a vaccine for common cold. And I'm not talking about flu, I'm talking about common cold. So the common cold is one of the examples where you let everybody, there's no treatment, and just at some point maybe everybody gets a common cold. Okay, so that's the model here. And I want to devote some time that we have. I will not cover pollution control model, although pollution control is also becoming popular because now we have a global climate thing coming in, and Biden is putting some money into global warming, but this is in some sense related to carbon pollution, but this one is related to a DDT production. So it's a slightly different model. And this model is due to two economists. Actually, one of them is a Nobel laureate, Spence. Spence is Nobel laureate. I think I met Spence at Stanford at one time. I was a postdoc there. So this model is a DDT model that is given by these guys, and it uses a phase diagram. I don't want to cover this, okay? And this is not included in the course. I just want to show you that this has again, a phase diagram. It's a different phase diagram than the other one, so I want to just show you the pictures quickly. As a global settle, we use, now here we use global settle point. We don't use anything more. So first time we did more effort, now a global settle point, so you can kind of use a global settle point to get that. And so I'm not going to covering this. I'm also not covering this. This is a new addition to third edition. This is a adverse selection model of mechanism design, and it's a principal agent model with model hazard, and it is I want to get to stochastic control. If we have time, we can come back to this, but it is also slightly how do I say it? It's slightly complicated unless you know a little bit about mechanism design to cover this, but it is also more important from the point of view of application, because when you have a type that is continuous, agent type that is continuous, then it is known that the problem can be formulated as a control theory problem. And it is a problem where the constraints are interesting. And if you look at the literature, it is very messy and very difficult to know what's going on. And my interest came in that Ashutosh Prasad was a marketing professor at our school one time, and I was in Hong Kong at the time. He sent me an email saying, "What do I do with this? I have this problem." And I told him that you need to put a constraint called a monotone constraint. You will see this kind of constraint. And that's that. And later on, when I came back, I found that there was a paper already done by somebody imposing that constraint in economics by somebody who was a professor somewhere, Austin or whatever, I don't remember. But then I forgot about this for a while, and until our operations management field, I wish I did not forget about it, because I could have been the early person to work in this area, but I didn't. And then the operations management people started applying mechanism design. Then I came back to it. When I came back to it, I thought that there's a lot of theory developed in economics, and all I could do is to put this together in a more understandable way. So I spent quite a bit of effort to write this section to bring you to a point where you can see how it is related to the control problem. Okay, and it's actually a lot. It's a lot of stuff involved in here, and try to make it. As you can see, you saw some papers coming in our lectures and seminars, individual rationality constraint and incentive compatibility constraints. So all these things are here. I also want to mention to you that when I was a PhD student, one of my committee member was an economist. And he gave me a working paper by Ekerlof called Market for Lemons. And I kind of I was working with something else, didn't really pay too much attention to it. And that paper got published eventually, and Ekerlof got Nobel Prize. And that paper became the main source of the idea behind the revelation principle that Meyerson came up with at Stanford. And so I do regret a little bit not going into the economics at the time when somebody gave me a paper, and I almost as much knowledge of control theory as Myerson might have. But anyway, those are some stories to tell. Um, I became more of an OM guy, OR guy instead of an economics guy. And one of my classmates who was in economics at that time was also working on rational expectation, which I also had some interest. Anyway, he got the Nobel Prize. So Finn Kidland was my classmate, and he received the Nobel Prize in economics for his work in rational expectation. Actually, not no. Lucas got rational expectation. Kidland got it, an application of rational expectation. Lucas was one of the professors that I interacted with, and I think he's quite well known. And rational expectation was way before I learned about it, and so these things were quite early compared to my work. Okay, so we are more or less done, and I want to tell you that we will now cover a new topic, which is stochastic control. Chapter 12 is a stochastic control, and when it comes to stochastic control, we don't do stochastic maximum principle. Stochastic maximum principle is difficult, not very useful in terms of solving problems. Mathematics is much more complicated, and only few problems have been solved analytically by using stochastic maximum principle. And one of my postdocs became an expert on stochastic maximum principle, and he wrote a book. His name is XYZ, Sun Yu Zhou. He was a postdoc for 2 years in Toronto. But that guy is a good mathematician, let's put it this way. And he's now a professor at Columbia. He moved from Hong Kong to Columbia. Now, what I will tell you is that the stochastic control problem uses dynamic programming or Hamilton-Jacobi-Bellman theory. So that's what we're going to do. And I would really appreciate that you read chapter 12. And in chapter 12, we use Brownian motion or Wiener process. I don't cover that. Wiener process is covered in appendix. So please read that. And all of you should take the course that Ben Susan is going to offer in dynamic programming. And he will do a lot more stochastic control than my one chapter. He will also teach you more on the Brownian motion and Wiener process, which is a new topic that I had asked the school to teach. And we wanted to find out whether Ganesh would teach or Ben Susan will teach. And Ben Susan is going to teach that. So it's a mathematical topic which is not possible to cover in my book other than in appendix, but Ben Susan will cover it. But I want you to just get some idea of stochastic control by reading this chapter 12, because you will know more about it when you take the course. So, and I told Ben Susan, he asked me if I cover some. I said, I do cover some, so people will know a little bit about what's going on. They will have some idea of Brownian motion, and so it will not come cold to you. And Ben Susan can then teach what he's going to do on. It's going to be a somewhat mathematical course because that's what he is. And at that point, I think we should call it a day, and we will do chapter 12 next week. And see you tomorrow also on the seminar on Friday.